to the spectrum. Want to accept it or not.
You had problems with like your singular values not decaying very well, right? And did you look at non-negative matrix factorization?
You're right.
We should, I'm sure it's all right.
Yeah, so that's Dean's brother, right?
Yeah, you
And
mentioned that.
Basically,
So that's-
its main killer case is when your singular values don't decay fast enough. Yeah, they don't have singular values. So that explains variance.
Okay, sorry for the delay.
Better.
We'll get the second day of the symposium started with Abinhav Giri from Ohio University. And he'll talk about active learning emulators for nuclear two-body scattering.
Hello, everyone. My name is Abinhav Giri, and I'm working with Dr. Elster, Dr. Risler, Jane, in building active learning emulators for nuclear two-body scattering. And today I'm gonna talk about what we have done so far in this project. And before we go there, I'll briefly go over what emulator is. Even though you guys know a lot of what emulator is already, but I already have slides, so I'm gonna talk about it. And then I'm gonna go over my emulator is based on T-matrix, so I'm gonna briefly describe what T-matrix is, and also our results. I will conclude after that results, I will conclude my talk. Okay. So we have, let's say, the main basis for emulator is when you have a big system, you want to solve out of that system, you want to solve this, you want to get your wave function or whatever this vector is, and you solve this multiple time, and you get your exact wave function. But if you wanna get for different, this Hamiltonian is dependent on this thetas. Let's say you wanna explore this theta space. That could cost you a lot of time and a lot of memory. In order to avoid that, what you want to do is maybe try to approximate that Hamiltonian using some snapshot metrics. Yeah. And how you build those snapshot metrics is you solve this Hamiltonian, you solve this equation, which is given on the left, for different thetas. You don't have to explore all these thetas space, but you can solve that for some number of thetas, and you do this projection and you get this smaller space. And with that smaller space, this process is called offline stage, and we build the reduced order model. From this full order model, we go to the reduced order model. And with that reduced order model, we can approximate our solution, like approximate our wave function, we can approximate our T-matrix with that reduced order model, and that will be online state. So this was just to illustrate more mathematically. Okay, this is how you build the emulator, this X matrix. You have, let's say, in full order model, you have your psi in higher dimensional space. In reduced order model, your psi is projected into this reduced space. And how you choose your thetas is was the main question in building this emulator. And there are actually two approach to do that. One is POD approach. In POD approach, you just select like lots of sampling points where you pick your snapshots, and you do SVD decomposition, and with that SVD decomposition, you will get your snapshot metrics. And the another way to do that is using greedy algorithm. In greedy algorithm, you start with the 1 point instead of lots of points, and with that 1 point, you have your snapshot metrics, and you emulate. You pick the highest you pick the point where the error is maximum, and you repeat that until you get your desired tolerance for that emulator. And this illustration is done in Joss' paper, which was recently published. And there are two types of greedy algorithm that I have done in my work. One is GROM and another is LSPG. I'll talk about those later. But let's go into the main thing that I've been working here. So Lippmann-Swinger integral equation. This is the T matrix equation where you solve this. Once you solve this equation, this boils down to this, which is basically a matrix equation. And if you are doing this, if you are just solving for the single channel, you already have this nice form to do the emulation. So that already looks like this equation. And but what if you are doing it in the couple channel? For couple channel, just to get the error nicely, we especially in our work, we instead of having like these two columns, we make this T vector of one row by using this block diagonalization of A matrix. And since we had our formalism in this way, I tried to first build the emulator based on the Minnesota potential, which is in the momentum space and given like this. And in this Minnesota potential, the V0 and V1 are the affine parameters. And you might ask why Minnesota potential? For the first time is the easier version. You don't want to directly go to the hard potential first time you do the emulators. So we did the emulation in Minnesota potential, and here is the illustration of the emulation. You can see this is in the two dimension, and here is it pointer, yeah. These number are the number of iteration that the greedy algorithm is going. Here I started with two random points in the sample space, and I pick and I do the emulation. With that emulation, there are errors approximated by this, and it chooses the highest point with the maximum error, and then it iterates through that until this error relaxes down to your desired value. And for this, I chose like my T matrix, my epsilon needs to be 10 to the power negative 10, below than 10 to the power negative 10. So it's approximating our T matrix with the exact T matrix up to 10 to the power negative 10 decimal places. So once we built that, we went to a little bit more complex chiral potential, and that chiral potential is given in this paper by Gazerdes, and we pick N2LO order, and since we are doing nucleon, our channel was NP, and for that NP channel, we had 9 low energy constants. So our sampling will be done not in 2 dimension, now in 9 dimension. So we are doing now greedy algorithm in 9-dimensional space in the momentum space. So for every greedy algorithm, there's a single channel, because we want to calculate, after doing emulation, we want to calculate phase shift, we want to calculate cross section. So For that, we want for every greedy algorithm, there's a single channel, triplet. For single channel, there's a singlet, there's a triplet, and the couple channels. So we have to do emulation for each J 3 times. Singlet, triplet, and the couple channels. So we are doing emulation in T matrix again. Once we have T matrix, we will get the phase shift and the cross sections. So this is the result for the phase shift. This is J equals to 1. Again, this is just the couple channel one. Here in our emulators, we already put one of the parameters is tolerance value. So we already defined, okay, emulation will stop when the tolerance reaches this. So the error needs to go below this. If all the errors are below that, then that's when the emulation stops. So you can see here the phase shift for 3S1, 3D1, they perfectly align up to some order. I didn't put the LSPG one because it will look the same. And here you can see the relative error. Relative error with GROM when the error tolerance is 10 to the power negative 7. You can see how that propagates into phase shift. If I define 10 to the power negative 7, in 3S1 channel is around 10 to the power negative 10, but 3D1 is 10 to the power negative 8. Same goes to the mixing angles here. If I define my error tolerance for GROM and LSPG, they behave similarly, and that's around 10 to the power negative 5 in this J equals to 1 channel, and I also have J equals to 2 channel. Again, 10 to the power negative 4, they behave similarly. It's around 10 to the power 4 or 10 to the power negative 5. For the 10 to the power negative 7, it goes from 10 to the power negative 7 to lower values. And also for the cross section, I did the same thing. We have our cross section with the XZ and the emulated one. Same GROM and LSPG with different tolerance values. You can see if I have 10 to the power negative 7, our cross section, the absolute mean relative error is 10 to the power negative 10. If I have 10 to the power negative 4, it's 10 to the power negative 6, around 10 to the power negative 6. So I can simply define my tolerance value to be 10 to the power negative 16 and be done with that, because I will get more precise cross section and precise phase shift. So why won't I do that? So you might probably already know it will take me the emulation part, the offline stage will take me more time if I define my tolerance value, because it has to go through more iteration. So this is just the preliminary check where when I move from 10 to the power negative 4 to 10 to the power negative 8, the time it takes for the emulator in the offline stage is 10 to the power, it increases by 5.3. And if I go from 10 to the power negative 4 to 10 to the power negative 12, it increases by a factor of 10. So you have to it costs more times. Sometimes it's not going linearly. You can already see that, but there's I haven't found the pattern here, and it was again the preliminary results. So maybe we can do more exploration in this. So up to this point, that's what we have been doing. And this is our future outlook. And in future, we want to build this. This was 2-body nuclear scattering problem. Now we want to extend this into 3-body and explore ND scattering. Then do more rigorous chiral interaction with phi uncertainties, and also explore this Bristol potential. And that's where I end.
Very much. Enough. Very nice. Dan.
Yeah, so my office mate does emulation for scattering too. And he works with rows, and from talking to him, he says he has to build a specific emulator per energy region. Do you have one single emulator or different emulators per region?
Yeah, for different energy, you have to emulate differently. Up to now, that's what I've been doing. Maybe in the future.
So not one single model that will emulate to all of energy range.
Yeah, up to now, if I change my energy, I have to again build the snapshot, but snapshot basis again. But it doesn't take too much time for that.
Curious.
Oh, you're here for the maybe.
Something. Yeah. So. I thought.
Yeah. Other questions?
While you're on this slide, do you have a sense of how accurate you need the emulator to be? Like, is 10 to the minus 4 fine for the quantities you're considering?
Yeah, experimentally, cross sections are up to 10 to the power. That's where 10 to the power -5. That's where they are compared to. But we want to be more precise. Let's say we want to be more precise.
So
That's
you
why.
might end up having to get down to 10 to the minus 7 or something. Or 10 to the minus 8.
Yeah, I did like 10 to the power -7 because in 10, most of the errors, like the number of iteration it takes for emulators to reach 10 to the power -7, let's say it's like 7, just 7 iteration. If I do just 10 to the power -8, it will sometimes take 14 snapshots.
Okay.
So that's why I was thinking, I want to just.
It's got a bit of a long tail.
Yeah, I just wanted to save my time and let's be done with it. Because it's not much, but it takes more time. So that's why I was doing.
Yeah. Thank you.
I can comment a little bit. I mean, there's one thing, for example, if you want to have experimental observables, there's an experimental error. And during my career, kind of, a theorist should get one order better than the experimental error. But there's also something else, for example, if you really want to go ahead now and determine parameters of a potential, you will have to have an error analysis and give an error how good you, the extractions of the chiral constants, you have to get that error. And so if you want to concentrate on that extraction, you may want to actually be a little bit more accurate in your T matrix so that you can focus on the error of your constants. So it's a little bit, what do you want to get out of it?
Thank you.
Other questions? So I actually had a question. Can you go back to the slide where you had the two-dimensional greedy points and you added gradually? Yeah. So I find this very fascinating. When Avik and I were studying this, we were interested in the actual contours of where the errors were the least. And we would find that if we have two training points here, then sort of in between those 2 points, there will be a minimum. You see sort of, right? But then you see some curvature, and that's actually sort of, I'm telling you something about the correlations as a function of the parameter space. So for example, you have some bending here, which it's trying to form a triangle, but it doesn't really form this triangle. Typically, that's what it would like to do if it was sort of, very linear with respect to the various parameters. But there's some curvature here telling you that there's some structure as a function of those parameters. Kind of interesting.
We have seen that structure, and my guess was just to like, okay, it's doing this Pythagoras thing, like if it's near that point, the error will of course be more or less than if it's farther from those points. But yeah, there's more than that's happening there, and I haven't explored those things.
Can you leverage that? So suppose that you compute the covariance matrix or something, then you diagonalize it, and you can find a linear combination of parameters which the covariance is flat. Yeah. In that case, it is really linear, like it's really uniform in there. So in that space, the parameters should be sampled uniformly.
Sure.
once you do this transformation back, it tells you exactly where to sample.
Yeah, you can make some predictions this way, for sure.
Okay.
Yeah. Other question, yeah, Jake.
Just a comment, like during one of our group meetings, Daniel Phillips had this interesting idea. What if we could trace one of these paths and look at the T matrix and how it depends on the low energy? Maybe we'll find that along those paths, the T matrix is actually very similar, or has a very
Yeah.
like a
It lives-
proportional
yeah,
structures.
That's likely true. Other questions, comments?
It'd be more so than along those paths that it's a linear combination of the training data, simple linear.
Yeah, that's right.
So have you thought about dealing with polar interactions, especially at low energy? The polar interaction,
Can you say that again? Sorry.
dealing with the
Polar
polar
interaction?
interaction.
Yeah, I mean, right.
Up to now, we haven't done that.
Not
Is
yet.
this new to be on?
Other questions? No, let's thank Abinhav once again.
Is that even doing it up here? Is a. How come Vita couldn't make it out here, do you know?
Thank you very much. Okay.
Third question.
Yeah.
That to some extent.
No, not really questions.
Manuel got really unlucky when we were getting all of our undergrad researchers. This was the only project that we covered. So we took a little.
All right, our next speaker is Nuwan Yapa from Florida State University, and he'll talk about towards scalable emulators for many body resonances.
I'll talk about this topic today. So this project has been sorry.
I don't think you want to mute that because people on Zoom now can't hear you.
I'm not doing that.
Oh, it's someone else.
Right now,
No, it's.
we have two computers in the system, so I'm just gonna.
Okay. So with my collaborators, we've been working on this project for several years now, starting with eigenvector continuation. So most of this stuff I already talked about last year. So this is going to be more like an update on the few things that has happened since. So to give you a motivation, if you look at the nuclei chart, you can see that most of the area is covered by unbound nuclei. So you can even say that resonances are more important than bound states. And like if you want to do ab initio calculations, methods like IMSRT has been already successful in attacking stable nuclei, but there's no such equivalent for resonances yet. So that's what we're trying to accomplish here. We can say that resonances are important to describe nuclei, actually decay modes, and there are different phenomena related to something like near threshold clustering, and then radiative capture is very important in astrophysics. So we want to understand all the stuff. So the overview of this talk will be something like this. I'll just give you a quick recap of the things that I've already talked about, and then I will give you a comparison to something called ACCC. And then finally, I will show you one of my naive attempts at PMM, since everybody seems to like that. Okay, so we are looking at resonances in this picture of gamma states. So basically, you can explain gamma states as the time solutions of the time independent Schrodinger equation with complex energy eigenvalues. So basically, if you let your eigenvalues to be complex, in addition to these bound states, so this is shown in the momentum space, in addition to these bound states and scattering states, you will have resonances over here on the fourth quadrant. So that will be our focus. And each of these resonances will have a real part and an imaginary part, and the imaginary part is governing the the half-life. So one of the more pedagogical ways of solving resonances is this technique called complex scaling method. So basically, the idea is this. So since you have a complex energy eigenvalue, the tail of your wave function tends to exponentially grow. But if you just take your coordinate and then multiply by some phase like this, you can convert this exponential growth to an exponential decay. So it looks like a bound state. So now you can use your already established bound states method for calculating resonances. And in the two-body picture, you can just understand this like a rotation of the scattering continuum by an angle of 2 phi. We are revealing these two-body resonances on the fourth quadrant. And if you go to the many-body picture, it's much more complicated, but still the idea prevails, which is that you will have different branch cut corresponding to each scattering channel. And what we are actually trying to solve are these genuine few-body resonances. We're not dealing with other channels yet. So we want to go from we're thinking about these Borromean bound states and genuine few-body resonances today. The idea is eventually we will try to use these bound states to extrapolate these genuine resonances. Okay. Another more sophisticated method is called the Bergen basis. Here, what you do is, so I suppose instead of this straight line contour, you just like curve it over to this line, like deforming the contour, but also you express everything in a basic. So in your okay, cool. Yeah, so in your basis, you will have bound states. So this stuff, resonances, and these continuum states. So the idea of this is when you have resonances in your basis close to this contour, you don't have to discretize this contour as finely as you would have to do otherwise. Yeah, so you can say the poles of the weight of the continuum, and also discretization, and of course you don't have these large negative, large imaginary things in your basis. It's much more numerically stable. Okay, so that's the Berger basis. You combine it with the shell model, you get something called the gamma shell model. Okay, so one of the first applications we found regarding this eigenvector continuation is using narrow bound states, narrow resonances to extrapolate broad resonances. Here I'm just showing you a toy model, a two-body toy model. So not only you can extrapolate these broad resonances, but you can go even below the contour of the basis. Something I forgot to mention earlier is when you change this contour, you have to still be below the resonances you want to target. But except here, thanks to EC, we can tackle resonances even below the contour. So that's one of the things we mean when we say that the reduced basis method, the reduced basis sometimes outperforms the original basis. So there's a very neat way to prove that this works. So if you just consider this contour given by C1, and let's say you are doing EC training over here, and they try to extrapolate this. There's no reason to say that this wouldn't work. This is about the contour C1. But now if you think about how EC works, you only care about the matrix elements given by this expression, and you only have an interpolation along this contour. And if there are no singularities here, you can actually deform the contour. You can make it smaller from C1 to C2, and none of these matrix elements would change. So the extrapolation would still work. So yeah, that's the argument.
Yeah, you're saying the third pole. So okay. We're training on this one. Without training in a sense. And that's what Abinhav was saying, it would work for in a sense. Yeah,
You would never get anything below the contour. That's
the yellow contour, you mean.
yeah. So if you were to do a full calculation with this C2, you won't get this.
Right. So if I deform the effect of X1, so there is no pole, so the integral is the same.
So it's simply
If there is no pole between C1 and C2, then of course I can deform the contour.
yes.
Then I get the same result.
Yes. Yeah. So yes. The idea is you can just use easy and use this contour. It's all these two resonances and then build an emulator on this to get anything below this.
Yes, so you are focusing on physical states, right? You're focusing on like the physical resonance state or bound state. But what about the other states? Because the other state really tells you effectively where the branch cut is. Do you know what
kind of other states do you mean?
the other state, right? So the spectrum is not just those resonance states or bound states. You have a bunch of discretized states.
Yeah, you will get some discretized states along this contour that you chose.
Tell you what branch cut is. Then we extrapolate to that the target states. Effectively, what you're doing, roughly speaking, right? So your effective branch cut has to be below the new branch cut has to be below the target states. But do you actually see that in your calculation? Because it's not
So there's
to do it.
funny thing is, so unlike your technique, I don't think you will see a branch cut per se when you build the emulator. It's just like it's not a sharp branch cut. It will eventually become worse and worse until it doesn't make sense anymore. There won't be a sharp branch cut below which you cannot extrapolate anything. You know what I mean?
This is the issue I have, right? When you talk about branch cut, you're talking about some function of energy. It's really not about an eigenenergy. It's not about eigenenergy. It's about a function of energy itself. And then you have branch cut concept. Now, if you put about the eigenenergy, it doesn't tell you those information.
Yeah, we can talk about this later. I'm not sure I understand the issue. Yes, thank you. Okay. Another way of extrapolating resonances is like follows. You just have your coupling constants. If you complexify the coupling constant, so that your pole moves over to the first quadrant, you can just train on those. You can just generate a random sample and build the emulator, and then turns out you can extrapolate the resonances very easily that way. So here, the orange dots are the exact values. The green ones are the extrapolated ones. And it works really well. This is very similar to Schilling's method, but not exactly. So the great thing about this technique is you don't need complex scaling, you don't need Berggruen basis. All you have to do is complexify your coupling constant. You don't need to analytically continue your potential. So it's quite cool. Finally, what we eventually want to do is something like this. So it's well known that if you have a resonance and you just tune your coupling constant to make it to make them stronger, sometimes those resonances can become bound states by moving this way. And in the Moeller plane, it will move this way. So what if we can convert this, turn these resonances into bound states and train on those bound states and eventually extrapolate the resonances? Unfortunately, if you just apply EC, so if you try to if you just train on the bound states and try to extrapolate these resonances, it completely fails. You can actually mathematically show that it fails because all the matrix elements are real. You cannot expect to get any complex values. But fortunately, we found a way to circumnavigate this. We call it complex augmented EC or CAEC. So I will not explain how it works, but basically it's a simple step. In addition to EC, you just take your training states and take their complex conjugates. And you can like qualitatively show that it should work. And that's explained in our paper if you want to look it up. Okay, so we have done some calculations using this technique. So if you look at helium-6, we're solving for the 0+ state of helium-6. We're just modeling it as a 3-body system with an alpha core and two neutrons. Simple Wood-Saxon potential, and then we just tune the interaction between two neutrons in this channel. So here, just naive EC doesn't work. If you increase, so if you do CIC with three training states, it works somewhat well. But if you go to 10 training states, it's nearly perfect, and this is the actual physical resonance that we want. Similarly, we can look at beryllium-6. So the idea is still same. It's a 3-body system. I mean, we are modeling it as a 3-body system, except you replace the neutrons with protons. The thing that's special here is that now we have a Coulomb interaction, which is not short range, and we can show both mathematically and empirically that still works. And this red circle is the physical resonance that you want. So eventually you want to go this route and eventually do something like nitrogen 9, which is a 5-proton emitter. Okay, so that's CAC for you. But CAC is not the only player in town. There's a method called analytic continuation in the coupling constant, or ACCC, and that has been around way before even when I was born. So you can read this book. There's a whole chapter dedicated to it in this book. It's a great book, and this whole idea is based on parity approximates. It is just a ratio of two polynomials. Okay, the motivation goes like this. So I didn't explain this part earlier. So what actually happens when you tune the coupling constant is that there will be a bound state, and there will also be a corresponding virtual state or anti-bound state, so to speak. At the threshold, they will actually meet, and they will become what's known as an exceptional point. And one of them will become a resonance, and the other will become something called an anti-resonance. So this is a square root type behavior. So so as a function of C, it forms this kind of a square root like Riemann surface. So it's a singularity, and if there's singularity, you cannot use Taylor expansions. So that's why you got to use something like parity approximates. That's what ACCC does. Yeah. So exceptional points are quite special because it's not just a degeneracy. Turns out your both eigenvectors also coincide. So it's a special phenomenon. But anyway, what they do is they simply take the momentum as a function of x, which is defined as the square root of c minus the c at the threshold, and then use a parity approximate to approximate the behavior, the trajectory of k, and then you square it, you get the energy, obviously. And in this thesis, there are a bunch of calculations with this method. So this is a neutron scattering in this channel, and when you go up to this order, it completely matches with complex scaling calculations. So yeah, it does work very well, but there's a limitation. The order of your extrapolation is limited by the number of training points you have, according to this equation. And I mean, if you think about it, you're only using the energy eigenvalues. You're not using the information in the eigenvectors. So you actually cannot expect it to perform better than CAC. And that's indeed what we see. I just did a quick 3-body extrapolation with 5 training points. And with 5 training points, CAC has already converged, but ACC is nowhere close. I think you need like 9, 10 points to get it to be acceptable. Yes.
So when you say analytic continuation, it's continuation of what?
You're continuing the momentum as a function of the complete constant.
Okay.
You feed it to the bound states and then you extrapolate the resonance. But there's one advantage here because it doesn't care about the number of particles, unlike EC. So it has O1 scale. That's the only advantage I can think of. Okay, so that's all about ACCC. And I was also we were curious about PMMs, and we want to see if we can do the same with PMMs. The idea is there are a lot of methods that in which we don't have the access to the eigenvectors, we only have the eigenenergies. So methods like ACCC and PMMs are applicable in those scenarios. And so how can we apply PMMs to this kind of a problem? We can either go with the usual way and define a fine matrix model, or we can take some inspiration from ACCC and define this kind of a square root form. I just show you so there's a big question mark here because spoiler alert, we cannot get it to work, unfortunately. We are curious why it doesn't work. The square root PMM, I tried with the 2-body potential, completely fails. My guess is it's because it has way more parameters than ACCC, so it's kind of an overfitting problem. So let's go back to the fine PMM, right? So if you just naively do this, it also fails because, obviously the emulator doesn't know anything about the system. It doesn't even know we're doing a physical system, let alone about resonance extrapolation. So it obviously fails. So we were curious if we can improve this. So what we did was, there's something known about the exceptional point phenomenon. It is that at the exceptional points, the Hamiltonian is not diagonalizable. So you have to do something called Jordan decompression. So when you do that, you get something like this with an off-diagonal element here. And these are zeros in our case. So what if we enforce our matrix model to take this form and let these parameters vary and keep these ones fixed? Unfortunately, that also doesn't work for reasons that we don't understand. Perhaps we're doing some mistake. Perhaps it's just the way it is. So we were expecting it to behave exactly as a bound state and an anti-bound state meeting and becoming a resonance and anti-resonance, but it doesn't work like that. Okay, so in conclusion, we can confidently say that EC-based extrapolation is superior when we have access to wave functions and Hamiltonians. But otherwise, ACC is always the best route to take compared to PMMs. And that's all I have. Thank you.
Yes. Very interesting work. So questions?
I think your method is going to work for general branching. It's not just square root. I can have a log.
Yeah, that's right.
So right now you have a square root of parameters, right? Yeah, square root of C.
Yeah.
I can have a log. I even can have.
Yeah, you can do anything, but just thinking was the ACCC is doing the square root thing, so that's what we can try those things.
But most of the time, actually numerically you don't know what that looks like. It really comes from analytic analysis. You know what the behavior of those points, but numerically you don't know actually.
Yeah, although square root is the simplest form.
It is simplest, but then if you get 2-body breakup, or even if you have Coulomb system, you actually have an essential singularity there.
Yeah, it's maybe true, but this is just a simple. What the calculation I showed is just a simple 2-body system.
Yeah, sure.
Yeah, this contour deformation is actually a very smart technique. Okay? But there's one thing, I mean, I did this way back for my thesis, but if you go, you have then to calculate your Hamiltonian in the complex plane. There could be, in some cases, there could singularities pop out in the 1, 2, 3, in the fourth quadrant, very far away.
Yes.
Did you check that? Is that happening?
The potentials that we use for these calculations doesn't do that, so.
That's, I mean, that
Yeah.
is the only thing that, I mean, it's, when I did this, I just calculate singularities and made a plot. Is there anything outside? And that depends on the potential. There's no guarantee how they are, but you have to check.
Yeah, of course, I agree. So with Gaussians,
Okay,
yeah,
with
yeah,
Gaussians,
yeah.
I would not expect it.
yeah, but if you had that problem, you just have to carefully choose the contour to avoid.
Yeah.
Then you'll be fine.
So how do you choose the contour, the simplest form ever you can think of?
Let me think. I think something like x times exponential minus x squared. Or for these calculations, I just took in the momentum plane 3 line segments, one going down, one going up, and this way. That's all.
Actually, there's comment here, right? So for the Bergen base, it's actually it's a little bit different from typical contour deformation. It actually has resonant state and the boundary
Yeah.
in the base.
There are two things different. One is the shape of the contour, and the other the base is expansion. Great.
Have you tried taking the eigenvector continuation matrix
Yeah.
that you get, perturb it a little bit, and use that as a starting point for your PML?
That's a good point, but yeah, no, that's
tell
a
you
good idea, but.
Because then you should just instantly find the eigenvector.
But the thing is, so with eigenvector continuations, the loss function is already 0 because you can get the training points exactly.
Yeah, but then I'm saying is you perturb it and then use it as the initial state for PML.
You really can train. But then,
The point
Might
is
not.
that the PMM solution space contains the eigenvector continuation solution.
yeah,
So it should just, if you just perturb it a little bit, it should just converge right back to your eigenvector.
exactly.
If it doesn't, then there's something practically wrong, not fundamentally wrong.
Yeah, and I'm asking if you tried that.
No, I haven't tried it.
So
Right,
basically,
interesting.
the PMN will find the branch count behavior, square root of C behavior. Should actually naturally build in.
The PMM is the eigenvector continuation if you
Yeah,
have
it's
the
naturally
eigenvectors,
built in.
right?
Exactly.
It has it.
So it shouldn't do worse than eigenvector.
Exactly, yeah.
I think you should, yeah, this is a great suggestion. I think you should look for is exactly what's going on when you have your complex augmented eigenvector continuation. You're taking the real and imaginary parts as separate pieces. That's why you're doubling up with the complex conjugation, right? So this is related to time reversal invariance. And I think that's probably not being captured in your PMM. You have to pay attention to how time reversal is being implemented here. By looking at your CAEC, that has that already built in. So if you figure out what CAEC is doing correct, and your general PMM is not, you might be able to figure out how to train your PMM restricted in some way.
Okay. I mean, I had to think about it, but thanks for.
Sure.
And there are many practical numerical hangups that, we encountered when implementing PMMs for the first time that you might have hit as well. So we
Yeah,
can talk a
what's
lot more.
happening. I was talking with Danny and I'm still learning how the whole thing works. Could be just some silly mistakes somewhere.
It's a shame that all the literature on training parameters through gradient descent is focused on real values only, because things change a lot when you have complex values.
Correct, yeah.
And anybody was special.
You switch to the Verdinger formalism of calculus that nobody knows.
Other questions for Nuwan? No, let's not go. At this point, we are just going to wait for Manushar Prakande to connect, our DOE program manager. He is supposed to join us around now, but we have essentially a coffee break until 11. So why don't we just do a coffee break until he connects, and then we'll.
Yeah.
Don't have
I tried the link that you sent me, it doesn't make it.
I know how bad it looks to